And now we finally get to Lagrange method. Hey guys, so I'm starting up again. So now I get to Lagrange method. So the problem I'm trying to solve, remember when I go back to my portfolio optimization, I want to maximize a function. So I'm going to call this my objective, subject to one or more constraints. So I'm going to use n for the number of variables of the function I'm trying to maximize, and then I'm going to think about having m constraints. So g1 up to gm. So there was a 18th century mathematician named Joseph Louis Lagrange who proposed the following method for a solution for this problem. And his solution was to make this function that's now a function of the original n variables, so x1 up to xn, and then also these values lambda, so you get one lambda for each of the constraints you have. So lambda is going to go, or the subscript on lambda will go from 1 to m, so there's lambda 1 for g1, lambda 2 for g2, and so on. And the way you make this function is you just put the objective here, and then you add lambda times each of these constraints to that objective function. So you have lambda 1 times g1 plus lambda 2 times g2 plus lambda 3 times g3 and so on. And also note that I've written the constraints so that they have to be equal to 0. So this 0 isn't a variable. That's kind of hard-coded in that spot. So if you have something like a condition x squared plus y squared equals 1, you have to write that as x squared plus y squared minus 1 equals 0. And then it turns out the optimal value, so the maximum value of f, the biggest or smallest I can make f, subject to these m constraints, is going to occur at one of the critical points for this function here. So just a little terminology to get us started. This function, capital F, so it's a function of the n variables and the m lambda values, is called the Lagrangian. And the vector lambda that has lambda 1 through lambda m as its components is called the Lagrange multipliers vector. So each one of these things is called a Lagrange multiplier, and then the whole vector is called the Lagrange multipliers vector. And then there's one necessary condition for this method to work. So if I rename the inputs to the original function, to the objective function, lowercase f, I'm going to put those in a vector and just call that x. And then if I let g of x just be this vector-valued function, so remember again when I put parentheses around a row, what I really mean is a column vector. So this is a column vector that has g1 as its first element, g2 as its second element, and so on. So it's a vector-valued function of the constraints. Then the gradient. And now remember that, so if I have a vector-valued function, the gradient's now going to be a matrix. The gradient of this vector-valued function, g of x, has to have full rank at any point where the constraint g of x equals 0 is satisfied. So that means you have to figure out what this gradient matrix looks like, pick a point that satisfies the constraint. So pick a point that satisfies g of x equals 0. Then evaluate the gradient at that point. So that'll give me a matrix now just of numbers, because it's a sort of a matrix of functions evaluated at one particular point. You can do elimination on that matrix, and you'd end up with a full set of pivots. So if that condition holds, then I say the rank of the gradient of this vector-valued function g is equal to m. So this matrix is going to have m rows. And so in each row, I'm able to find a pivot. That means I have full rank. And so I said, oh, you can do that for one point. But actually, for this condition to hold, you have to do it at every point. So this can sometimes be pretty problematic to do. Most of the time, I don't bother checking this unless something really goes wrong, and then you wonder, why is this not working? You know, oh, maybe it's the condition isn't being held. Okay. So the Lagrangian is going to be a function that has n plus m variables. So x is this is the argument for the objective function, little f, which was a function of n variables. And then I'm also going to have m Lagrange multipliers. So the Lagrangian has n plus m variables. And I need to compute the gradient of this thing because I need to find the critical points, because what I'm after is a critical point of the Lagrangian will correspond to an extreme value of my optimization problem. So I can think about doing this in two steps. And it turns out this step is pretty easy. So I'll write d sub x of the Lagrangian. So this will be the gradient, but I'm only going to take partial derivatives with respect to x. And then this will be the gradient with the partial derivatives with respect to lambda. And since this should just be one long row vector, so it's a row vector because I'm using the square brackets here. So I mean I want everything to stay in a row. And the first n elements will be these partial derivatives with respect to the x variables. And the last m elements will be the partial derivatives with respect to the Lagrange multipliers. And now let's remember what the Lagrangian looks like. And now if I want to take the partial derivative of the Lagrangian with respect to one of the x variables, what I'll end up with, because the differentiation is a linear operation, so the derivative of a sum is the sum of the derivatives. So I'll have one derivative. So if I'm taking the partial with respect to xj, I'll end up with the partial derivative of little f with respect to xj. So that's my first term here. And then for lambda 1, I'm going to end up with lambda 1 times the partial derivative of g1 with respect to xj, plus lambda 2 times the partial derivative of g2 with respect to xj. So I can actually just move that differentiation operation across the sum, and what I'll end up with, partial derivative of f with respect to xj, plus the sum from 1 to m, so summing over each one of these Lagrange multiplier terms, of the Lagrange multiplier, so lambda I, times the partial derivative of constraint I with respect to xj. And then on the right-hand side, this turns out to be quite a bit easier. So when I'm taking the partial derivative with respect to each of the lambdas, the objective function doesn't have a lambda in it. So the derivative of this, the partial derivative of this with respect to any one of the lambdas is going to be 0. And also, the g doesn't have any lambdas in it. It's also a function just of the x variables. So the only place the Lagrange multipliers are going to show up are just lambda I to the 1. And so when I'm taking the partial derivative with respect to lambda I, every one of these is going to be equal to 0 except for lambda I. And so what I end up with is just gi of x. So the gradient of f is going to be these partial derivatives with respect to x. The gradient of g is going to be this, so it's a little tricky to see, but there's n columns, so x1, x2, all the way up to xn. And then there's m rows, so it's an m by n matrix. And then each row is just going to be the gradient of gi of x. So here, first row is the gradient of g1, second row is the gradient of g2, and so on. So I end up with this matrix being the gradient of a vector-valued function. So now I can express the sum in the second term using matrix notation. So I had this sum of lambda I times the partial derivative of gi with respect to xj. And so if I look at a column here, if I pick a particular j, so suppose I pick j equals 2, that's going to be the second column of this matrix. So this sum is just going to be equal to lambda times the second column of this matrix. So that's what I mean when I say matrix sub j. I mean the jth column. So if I put a little 2 down here, I'd be talking about the column vector that's the second column of this matrix. And I can write this sum then as lambda transpose times that specific, so the jth column of this matrix. That's going to make my notation a little bit easier to handle now. I don't have to write out all of these partial derivatives. I can just write it out in terms of gradients. So it follows that my gradient for the whole Lagrangian now, this is going to be the gradient of f plus this thing that I just worked out up here. And so I'm going to be able to do this plus operation because the gradient of f is going to be a row vector with n elements. And then lambda transpose, that's also going to be a row vector with n elements. And I'm going to multiply that by an n by n matrix. So it's going to stay a row vector with n elements. So this term is a row vector with n elements. This term is a row vector with n elements. And so I can do the sum just by doing the summation element-wise. And I end up getting exactly what I had in the sum formula on the previous slide. And then the derivatives for the part of the Lagrangian that just corresponds to taking derivatives with respect to lambda, they just end up being the constraints again. So remember, g was a vector-valued function of the constraints. So if I take g transpose, that's just going to be that same vector but put into a row. And I have to do that because this whole thing has to end up being a row. So I end up with a row vector here of n elements and a row vector here of m elements. And so when I put those two next to each other, I end up with this row vector with n plus m elements that's the gradient of the Lagrangian.